Bellman, welcome. Hello, Tristan, welcome back. Good morning, Jordan. Hello, Kai, welcome back. Hello, Zin. Good morning. Welcome back, Irvin. Hello, John. Good morning. Santino, welcome back. Good morning, Asim. Welcome back. Hey, Tintin. Good morning, Nadal. Joseph, welcome back. Hi, Michael. Welcome. Hi, Joseph. Welcome back. Hello, Kim. Hi, Nadina. Good morning. Joy G, welcome back. I hope you're doing well. Hi, Emma. Welcome. Good morning, Wendy. Hey, Frank. Welcome. Leo.
Hey, Mr.
Welcome
Brown.
back. Thanks for coming on time, Leo. Hello, Ryan. Hi, Faith. Hey, Alex. Welcome back. Welcome back, Alex. Hopefully the journey went well. Hi, Jumila. Good morning. All right. Thanks for letting me know, John. Please watch the rest of the video later if you can. Hi, Phil. Good morning. Welcome back. Perfect. Welcome back. Hope you guys are staying warm, staying well, having a good day as well. Pretty windy day out there yesterday, and hopefully you have power. Seems like you guys have power. Hopefully not running on like the red of your battery of your Chromebook or laptop or your cell phone, whatever it may be. So yeah, we're back at it. Really windy all night last night in my house. A couple limbs down. Power lines obviously are okay. We weren't cut short with power, so we're in good shape. Hopefully you're okay. Hopefully your houses are okay. Hopefully it get damaged. Cars damaged, all that stuff. But here we go. It's definitely a cold day out this morning. I'm looking for a few people, actually just one person now. Hey, Alan, welcome back. I'm looking for Micaiah. If you're here, please let me know. All right, I have a different angle here today on my little setup. Why? Because I'm going to do a demonstration a little bit. But before I get to that, I just want to refresh everybody, a little heads up. Elementary students will be returning back to school on Monday. So if you have a younger sibling, brother, sister, cousin, whatever, that lives with you, hopefully you could inform them in case they're not getting the information from the school. So this Monday, elementary students, it's going to be March 8th, elementary students have the ability to go back in person, teach and learn in person. But again, they have two different cohorts, two different groups are broken up. And by now, you probably should have gotten some information, your parents, about which cohort they're in. Cohort A, cohort B. Cohort A goes Monday and Tuesday. Cohort B goes Thursday and Friday. If you haven't received information, you may want to tell your parents, guardian, whoever's at home, call the principal, call the school to figure out that information. And another thing, I'm not trying to push you one way or another, but if your parents, guardian, grandma, whoever's not ready, if someone's not ready to send them back to school, you have the ability to opt out of it and just continue that virtual learning as well. Oh, I thought I talked about that a few times. Someone asked me, are kids going back 1 time or 2 times a week at Proctor? Proctor, as of now, Proctor High School is different than middle school. It's different than the elementary school. Proctor High School, since we have 2,600 students within this building, they had to break it up so the numbers would be appropriate, so they meet the guidelines from the CDC for proper social distancing. We can't have 1,000 people in the building. That's too many people. It exceeds the proper social distancing of 6 feet, all that stuff. So the maximum number of students that are going to be allowed in school is like 560. So each cohort, there's 5 different cohorts for Proctor. So this is only for Proctor now. This is a game plan as of last board meeting. They may have changed it. I don't know. So Proctor's population was divided up into 5. So they had 5 different cohorts. It happened to work out there's 5 days in a week. So they divide it in 5. How did they divide it? I didn't talk about this last time. They did announce they're dividing it by alphabet. So they're taking a fifth of the alphabet, cutting it in half, no matter what grade you're in, 10th, 11th, 12th, whatever grade you're in. I don't know the range, but maybe A through E is cohort A. I didn't do the fifth of the alphabet. But take the fifth of the alphabet, and that's where it's going to be divided by, and it's alphabetical order. So if you're A and Z, your last name's A, but your friend's last name is Z, you're not going to school with them. They're not going to flex that at all. So don't even try that. Don't say, hey, I can't come this day, because they're not going to. They're not wiggling with that at all. Sorry. Yeah, so that's how they're dividing it. Again, from what I understand, you guys have the ability to either continue virtual that one day or come to school. It's not a bad idea. It's going to be a small population. Proctor's going to look a lot different with that population being decreased so much. So to answer your question, once we're broken up the cohorts at Proctor in 5 different groups, A, B, C, D, E, you come that one day a week. That's it. So one day a week until things change. Yeah, they announced once the CDC changes their guidelines for social distancing, that stuff, then they'll bring back the bigger and bigger and bigger population as well. So for now, it's only one day a week for high school. Middle school is different. Elementary is different as well. So yeah, hopefully your parents, or if you want to watch the meetings, you can. For the board meetings, they're live for everybody. Yes. Somebody else asked, here we go. The teachers are going to be teaching online and live at the same time if the students come to school. Yes. I believe, I'm not 100%, I'm pretty sure though, elementary is doing the same type of routine. So basically the teacher would be up in the front of class teaching, and there's going to be, in my situation, there's going to be like 5 kids, maybe 5 kids in class on a day. And then the rest of everybody else, like 22 other people, will be live on the computer. So what am I going to do as a teacher? What do I plan to do right now as a teacher? My majority of my population is online. I have 5 people in front of me. That's cool. I'll definitely interact with them too. But my majority of the population's online. I will have like a computer here, and I'll be like doing something like this. I'll talk to the class and talk like this. But majority of this will be like very similar to what I'm doing here. I'm not going to disservice you guys at home for not being in class. If the majority of the population's online, I believe I should teach the majority of the population online. Most of the time I'll do that. But when we have like time to work on exit passes, you might not see me as much online. I might give the people in class more attention for one-on-one help, so I can interact a little bit more. So stuff like that. So yes, it is supposed to be live instruction from the teacher, regardless if you're virtual or if you're in class. So that's what it's supposed to be. Will all teachers do that? I don't know. I will be. I'm doing my job. Hopefully you're doing your job at home as well. As of now, the regents are still playing, so I'm still going to do my job. If you're doing your job, we're good. We're in good shape. By the end of the year, you should feel confident about this regents. Just going to throw it out there. Not too many of my students that actually do the work don't feel confident in the regents. If you're doing your part, you should feel confident with taking the Regents exam. You should see these questions a couple times before. I take all my questions for the Regents exam. A lot of times they do repeat for chemistry. And I can predict, you should be able to predict the Regents types of questions at the end of the year too. Anything else for me? If you have more questions, feel free to ask, and I will ask my department, the department chair or assistant principal. If you have more questions regarding the opening of Proctor, they told us to have you guys contact the AP, your AP, your assistant principal, and they should be able to address your questions. They would, Joe, they did not tell us a specific date. So if someone asks what date you think will come back, they don't want to say a specific date because then people are going to get like, oh, crazy, all crazy about it. Say, oh, we're heading back April 4th, April 5th. They don't want to do that because it might change. There's a lot of different variables that have to really get ironed out before we get there. Yes, March 8th is when elementary starts. From the board meeting, they said they want to try that out for a couple weeks, and then maybe March 22nd have middle school come back. And then they said, yeah, they want to try that out for a couple weeks, and hopefully, if all goes well, they'll push for rough estimate. Looks like April 5th to me if they said 2 weeks. April 5th is the date for return. So I know you guys are all on different aisles of coming back or staying home. You have to do what you feel best. You have to do what your family feels best is the right decision. I'm not going to tell you what to do. I'll be here. If you decide to come back, we'll be safe. There's not going to be 27 people in my classroom at once. That's a guarantee. There will be people in the hallways when you walk, but that's on you to be smart, not get too tight with people, I guess, not to get too close, not to smooch, no smooching in the hallways, all that stuff. So be smart, be safe. If I can help you out, let me know. Anything else? So I can't give you a date. I don't know. I don't know for a fact when we're going to come back. Busing's a little bit of an issue, so. Anything else? A lot of housekeeping today. Kai, I'm just looking for you if you're here. All right, let's figure out what's going on with the COVID report for today. Looks like our governor got himself in a little bit of a hot seat. We'll see. They might be false accusations. But he's in a tough situation right now with nursing homes numbers, and he's been accused of a couple things as well. I don't want to say anything about that. Hopefully it's not true. Moving on forward, the total active cases for Oneida County is 608 active cases in the county. We have 18,459 resolved cases in the county, and we added another death since the last time I seen you guys. So that stinks. Another family is impacted by this COVID crisis. Hospitals, there's 36 people in the hospital, and there's another person in ICU. There's 10 people in ICU. Still, these healthcare workers are really stressed still. Think about how it was before COVID for these healthcare workers, a nurse that didn't have to deal with COVID. Then this pandemic hit. Think of how their lives, their occupation, their job changes. Their daily routine has changed since this COVID. So they still have 36 seems like a low number. It's still a stress on them. You can check out the vaccine numbers. I already talked about Johnson & Johnson news vaccine. Here's a number of daily cases, in our county. Last piece of information, the 28th, we had 22 cases. Good sign. That's good stuff right there. So hopefully, remember I told you like right over here, I was like worried. I'm like, what is going to happen? What's going to happen? I said we go up, down, level out. That's the three options that could happen. But it's jumping around a little bit. You're going to have some peaks. You're going to have some valleys in that range. So 22 on the 28th. 27th was a high value of 59. The day before was 29. The day before that was a high value of 52. So looks like we're getting closer to a lower average. Last 3 days are good data. So we got to control this. Hopefully, as a community, we get down below 30, below 20, below 10, get back into it. From what I understand, someone asks, is the vaccine actually working? I'm going to trust science. I'm definitely going to trust science on this one. In order for a vaccine to get approved by the CDC, there are so many different guidelines, so many different steps it has to be approved before they push it to the American population. So the people of America, there's a lot of tests that these vaccines, the Moderna, Pfizer, Johnson & Johnson, they had a whole year to work on these vaccines, almost a whole year. But they've been working on these vaccines. These scientists have been working on these vaccines for a long time. Why was it beneficial? Why is it beneficial for scientists of these companies to come up with an effective vaccine? A lot of money. So these scientists worked their tails off to come up with a vaccine, and the companies wanted their scientists to come up with a vaccine so they could generate and make a lot of money. Think of all the people that are going to have this vaccine. Someone's got to pay for them. We're not going to be paying. We're not paying for them, but the government will be paying that company for all those vaccines. So it's still, regardless, even though it's a race for like that money, it still has to go through the checklist of all this criteria for a vaccine to be approved by the CDC. Yeah, it had to feel rushed. If we didn't really rush into this vaccine, or we didn't really put the foot all the way down the gas pedal, then this COVID could still be like the numbers of January 1st or close to it. But yeah, you could check out some stuff on vaccines, read up on stuff if you're inconsistent or not sure about it, unsure about what to do. Read up on it, check out the CDC guidelines for vaccines. It's pretty rigorous what it has to go through. Good questions, though. All right, let's figure out what's happening in chem class today. Here we go. Welcome on back. I threw a lot of attachments up here. We'll go through a few of those. Welcome back. The quote of the week comes from William James. Act as if what you do makes a difference. It does. Whether you succeed, whether you fail, whether you do well on a test, you don't do well on a test, get in an argument with your brother, sister, grandma, whatever it may be, mom, dad. What you do, act as if what you do makes a difference. Everything you do makes a difference. Whether it's good, whether it's bad, that makes you you. Learn from mistakes. All right, today's Tuesday, March 2nd, 2021. Today's a day 2. We are continuing on with Unit 7, which is Kinetics and Equilibrium. We're going to continue on with Topic 3, exo and endothermic reactions. We'll do that for the next couple of classes. I will start off with a demonstration. We'll go through some examples on PE diagrams. I'll give you time to work on the exit pass. And hopefully we'll get through the examples of topic number 3. But that will be probably as far as we'll get today. Next class, we'll give you time for the exit pass in topic 3, and we'll go through this table on table I on heat. But we've been talking about potential energy diagrams and exothermic and endothermic reactions. I do want to talk about a couple attachments here, like this one right here. So some of you guys turned it in. You didn't have to turn it in, but this is the online resource for the chapter for this unit. It's on kinetics and equilibrium. So you guys have this realized here. I am not positive of what you see on your end. But chapter 18, hopefully you can find chapter 18 somewhere. I'm guessing you have something that looks like this. But the online student edition is the one that really draws my attention. I like this one. If you click on that, this is your textbook for the year. So there's a chapter. I've been adding these throughout the duration of the year. Here's your chapter 18. It's like logging a textbook home and bringing it out all the time. This is your textbook. you can see the different topics. So it's kind of like topics here. Take those things. All right, so you can see the different topics that they have outlined here. They're kind of similar to mine. Topic 1, rates of the reaction. Topic 2, progress of a chemical reaction. So potential energy diagram will be in that topic. You see where topic 3, 18.3, reversible reaction to equilibrium. We'll get there. We'll get to solution or solubility equilibrium. We'll get through entropy as well. So hopefully you can see the outline of this textbook. If you scroll on through a couple pages, the big ideas you should understand by the end of the unit. How can a rate of a chemical reaction be controlled? How could you speed up or slow down the rate of reaction? You should be aware of that one a little bit. And you can obviously see that there's different texts here that correlate to the topic. Again, if you need a little bit more reassurance on a topic, you could find that topic in the text. You could read it, or you could listen to it.
Collision theory. A model called collision theory is used to relate the properties of particles to the rates of reactions. According to collision theory, atoms, ions, and molecules can react to form products when they collide if the particles have enough kinetic energy. Particles that do not have enough energy to react bounce apart unchanged when they collide. Figure 18.4 shows what can happen when hydrogen and oxygen molecules collide. You can use 2 balls of soft modeling clay to illustrate collision theory. If you throw the balls of clay together gently, they don't stick together. This situation is analogous to colliding particles of low energy that fail to react. If the same balls of clay are thrown together with great force, they will stick tightly to each other. This situation is analogous to the collision of 2 high-energy particles that results in the formation of a product.
All right, so obviously it'll read that topic to you if you want a different understanding. So feel free to check that out. You can figure out activation energy. Oh, that defines it right there for you. That's pretty cool. Minimum energy colliding particles must have in order to react. Oh. Gives you Spanish if your first language is Spanish. You want that instead. It gives you a definition for activated complex. That's cool. Guess I didn't know that. So it defines those as well. You can find more information about potential energy diagrams, exothermic, endothermic reactions. You should know the factors that affect the rate of reaction: temperature, concentration, particle size, which is surface area, and pressure. The 4 factors that affect the rate of reaction. But my main thing is, it's here for you if you need it. If you want to use this resource, it's here for you. There's the text. All right, let's move on forward. Let's get a little bit more information about exothermic and endothermic reactions.
In today's video, we're going to look at what exothermic and endothermic reactions are, see how we can represent them using reaction profiles, and finally, consider the importance of activation energy. Now, the important concept to understand in this topic is that different chemicals store different amounts of energy in their bonds. For example, if we took the reaction methane plus oxygen to form carbon dioxide and water, then each of these different molecules would hold a different amount of energy. Or in other words, they'd each have different amounts of energy in their chemical energy stores. What's important to us, though, is how much energy all of the reactants have in total compared to how much energy all the products have in total. In this particular case, the products would have less energy than the reactants. And we can show this on a reaction profile, where the y-axis is the total energy of the molecules, and the x-axis is the progress of the reaction. So on the left, we place our reactants, and on the right, we put our products. But importantly, for this reaction, we'd have to put the products lower down, because they have less energy. Now, if the chemicals in the reaction have lost this much energy, then this much energy must have been released to the surroundings. Because remember, energy can't be created or destroyed. It can only be transferred from one place to another. And the most common way to exchange energy with the surroundings is in the form of heat. In this reaction, lots of heat energy would be released. So if we had done it in a sealed container, then we'd be able to measure the increase in temperature as the reaction progresses and releases heat energy. We call reactions like this exothermic. And what all exothermic reactions have in common is that they transfer energy to the surroundings, usually in the form of heat. The most common type of exothermic reaction is combustion reactions, in which fuels are burned, usually in the presence of oxygen, like in our reaction. Other examples, though, include neutralization reactions between acids and bases, and most oxidation reactions. The opposite of an exothermic reaction is an endothermic reaction. These are reactions which take in heat energy from the surroundings. For example, if we wanted to break down calcium carbonate into calcium oxide and carbon dioxide, we'd have to supply heat, perhaps by using a Bunsen burner to heat up the solid calcium carbonate. So if we wanted to draw a reaction profile for this reaction, then just like before, our reactants would be on the left and the products on the right. But this time the products would be higher up because they have more energy than the reactants. And so we'd label this difference as the energy absorbed rather than the energy released. So far we've covered what exothermic and endothermic reactions are and looked at the reaction profiles for each, which you might have to draw in the exams. The last thing we need to cover is activation energy, which is the minimum amount of energy the reactant particles need in order to collide with each other and react. So the greater the activation energy, the more energy that will be required to start the reaction. We can show this activation energy on our reaction profiles when we draw a curve from the reactants to the products to show how the energy changes during the reaction. Specifically, this increase in energy from the reactant's energy level to the highest point on our curve is the activation energy. So as you can see, even in an exothermic reaction like this one, which releases energy overall, some energy is still required to get the reaction going in the first place. We can do the same thing for endothermic reaction profiles. Again, we draw our curve, and the activation energy will be the difference in energy between the reactant's energy level and the very top of our curve. This means that if we wanted to show the same reactions, but with slightly higher activation energies, then we'd just make our curves go a bit higher. Whereas if we wanted to show lower activation energies, we'd just make them a bit lower. Now, the very last thing to say is that if you're drawing a reaction profile for a specific reaction, like the ones that we discussed earlier, then instead of just writing reactants and products on the lines, we can actually put the chemicals from our equations. Anyway, that's all for now. So hope you enjoyed it, and we'll see you next time.
Okay, so there's a little bit more insight on exo and endothermic reactions. I'm gonna change my view a little bit. I'm working on a demonstration. Next portion of class. Okay, I hope you could still hear me. I took my headphones out. All right, I'm going to do a demonstration today on an exothermic reaction. So this exothermic reaction, what's going on here? We're going to be analyzing this right here. You have 2 moles of H2O2 yields 2 moles of water plus oxygen gas, O2, diatomic molecule.
In this reaction, you have obviously the y-axis is potential energy in kilojoules. The x-axis is the rate of reaction. So here we go. We have the reactants, first part of the reaction, reactants, yields the product. There's my product. We should know that. Reactant to product. Forward reaction. We have potential energy of the reactants. Top of the reactants to the bottom. We have potential energy of the products. Top of the product to the bottom. We have activation energy is the energy needed to start the reaction. There it is. Activated complex. If you jump on this roller coaster, it gets complex at the top, then it falls back down. Complex, the top of the peak, all the way to the bottom. The heat of the reaction, the change or the difference between reactant and the product. So let's go ahead and perform this reaction. So here we go. First things first, I'm going to put some safety goggles on. Get back to class. We do some labs. We open up a little bit more. We'll definitely do more of these demonstrations or labs. You'll be required to wear lab goggles. Here we go. A little bit big on me. So here we go. Going through this reaction. What I'm going to do here, I'm going to take this graduated cylinder. It's a 100 milliliter graduated cylinder. And I'm going to add 20 milliliters of hydrogen peroxide. So this hydrogen peroxide is a little bit different than the hydrogen peroxide that I use at my house. Remember, I had like a brown bottle for 99 cents. We looked at that for solutions. This bottle is like a little bit more expandable, contractible, like an organ style bottle. And why is it like that? Because when the hydrogen peroxide heats up or cools down, it's going to start to expand or contract. So there's a little bit more flexibility in this bottle. I'm going to take 20 milliliters of hydrogen peroxide, H2O2. It says on here it's 30% of the solution. What's that mean? 30% is hydrogen peroxide. The other 70% is going to be water. So I'm going to take 20 milliliters, roughly 20 milliliters. So this hydrogen peroxide you cannot buy at Walmart. You can't buy it at the drugstore. If you go to a hair and beauty place, I haven't been there much. If you go to a hair and beauty place, you could probably find a higher concentration of this volume. Why? Because they use the hydrogen peroxide for hair coloring. All right, so I added a little bit more. I added 22 milliliters. So when you take a reading, what you want to do, you want to pour it, and you want to get low, get low, get low, get low, get low to the flow. You want to look down at the meniscus just to check that curved line is going to be equal. So you want to make sure that meniscus is at the right level. Next up, I'm going to drop a drop of food coloring, red. Right now, nothing crazy is going on. You have a heterogeneous mixture. Next up, I'm going to add some soap. So right now, hydrogen peroxide, food dye. Now I'm going to add some soap into the solution. So all it is dish soap. I'm adding about 10 milliliters of the dish soap. Once I pour this in, you'll see that starting to turn into a homogeneous mixture. It's like starting to stir. It's mixing a little bit more. And the last thing that I have to add, so last thing I need, which is not in this equation, this is going to be my catalyst. This is going to make the reaction happen at a quicker rate. So this catalyst is sodium iodide. What's the catalyst do? It speeds up the rate of reaction because it's lowering two intervals. It's lowering my activation energy. It's lowering my activated complex. So last thing I'm going to add is the solution of sodium iodide. It's a 2 molar solution of sodium iodide. I'm going to add 5 milliliters, the small graduated cylinder. So I rest my fingers on the bottom just so it doesn't tip over. You don't want to get it on you. Obviously, you don't want chemicals to land on your body, your flesh. Once you get a little closer to the volume you have, you want to get low and check it on out. Make sure you're at the meniscus. We did this in the beginning of the year. We measured out volumes in the beginning of the year. You know how to accurately record volume. Hopefully you can measure as well. All right, so the last thing I'm going to do is I'm going to add this catalyst to this larger graduated cylinder, we'll have a reaction start to form. So once I pour this in, the amount of collisions, the effective collision is going to increase immensely. So what's going to happen, as I pour this in, these particles are going to start to collide, have more effective collisions. They're going to be oriented correctly. There's going to be more energy in the system as well. So it's going to have a ton of these little effective collisions going on here to proceed to the product. So here we go. Last part of the reaction. Let me move you guys in closer for a second. Okay, last part of the reaction. Here we go. Starting to happen. Here we go. Maybe you could see that there is some heat being generated here. So heat is definitely given off in this reaction. You can see that happening. It's exploding here. You see this reaction here? You have in this, you can figure out it's going to be water and it's going to be oxygen gas released in this situation. Those are the products of this reaction. The presence of heat in the situation, you can't really see it as much now, but it still is, it is definitely warm if you bring your hands closer to it. That presence of heat was being released in that situation. You could see it's going to be an exothermic reaction. So if I had the value for heat there, the heat would go right here in the chemical equation. This equation looks like a decomposition equation, or you could say it's going to be an exothermic reaction. All right, that's called elephant toothpaste or old foamy. There's a little demo for today.
Hey guys, how we doing? Hopefully you enjoyed that little demo. But anyways, that chemical reaction, definitely an exothermic reaction. I do want to actually look at one more video on what just happened there on elephant toothpaste. So this is Jimmy Kimmel, and he does has someone come in to do the experiment of elephant toothpaste. Enjoy.
Our next guest is an educator who will surprise, delight, and possibly endanger you. He's here tonight to share the wonders of chemistry and physics. From Boston, please welcome Science Bob Flugfelder. Hello, Science Bob. Thank you for coming. That's a good-looking jacket you have. Is that a tie-dye?
It is tie-dye, yeah.
Can you buy that, or you have to make that?
I actually made that.
You made that?
It's the first and only thing I've ever tie-dyed.
Well, you know what? It's a winner.
Thank you.
So tell us what we're going to do here.
All right,
I know you're a teacher.
Yeah.
What grade do you teach?
Elementary level, which
Okay.
is somewhat unique.
And the kids go nuts they like to see weird stuff happen.
Oh, yeah, yeah.
Me too.
We don't sit and read a whole lot.
Yeah, that's me either. That's exactly what I like. So that's why this is going to work out so well. What is our first experiment?
All right.
Is it really an experiment?
No, it's a demonstration.
A demonstration. Okay,
Yeah.
very good. All right.
All right, so we're going to do a little, we're going to basically break apart molecules.
Good.
Yeah. And we're going to use hydrogen peroxide, but it's not what you get in the store. Hydrogen peroxide is actually H2O2.
Okay.
So H2O is water. They put an extra oxygen on it, and you got hydrogen peroxide.
You get a weaker version in the store?
Because
I used to intentionally cut myself so I could pour
the bubbling?
so I could sizzle up my...
Yeah, the stuff that we use will actually give you a chemical burn.
Okay, so don't use it.
Don't.
Okay,
Yeah.
great. All right. So, all right, so what do we do?
We're going to get started. We're going to start with a little bit of, actually, dish soap. So if you want to put some dish soap in your flask.
How much? Just a squirt?
Yeah, a little more. That's good.
Okay.
So dish soap will keep the bubbles, because we're going to remove the oxygen. They'll hold the oxygen.
Okay.
So I'll put a little bit in here.
Mm-hmm.
All right. Next, coloring. We have green and red. Do you have a preference?
I'll take red.
All right.
Be very Christmassy. How much of this?
And just keep going. Keep adding a lot of that.
Okay.
That's good. A little more.
This is going to be delicious.
All right.
Is this how you did your jacket?
That's good there. Okay. All right, so I'm going to add the hydrogen peroxide because you don't want to do that.
Okay. Oh, it's dangerous, right? Okay.
And actually, yeah, let's get all geared up here.
Okay, good. Put these on my eyes.
There we go. All right, so in goes that.
Mm-hmm.
And
Now, what's happening here? What process are we about to see?
So here's what we're going to see. We're going to, in order to remove the oxygen, we're going to use a catalyst.
Okay.
The catalyst will speed up the reaction. So that's what's in here. It's a sodium solution. We're going to pour that in, and that's going to remove the oxygen. The soap is going to hold it, and
we're going to smother to death, all of us.
It'll be okay, but it will create a lot of bubbles really fast.
Okay, great.
And usually this is done in graduated cylinders, but we're going to make it a little more intense with these ridiculously large flasks.
Okay, good.
All right. So this is what you're going to use. We're going to pour that in there. The oxygen will be released, and we'll watch the reaction. We're going to need to step back after we pour.
Okay.
All right. Here we go.
Step back.
Ready? In 3, 2, 1, pour. There we go.
Whoa! Whoa! Wow, that's great. It's like Ghostbusters. Wow. Whoa! That's something. We got slime. Whoa! That's going to be coming down for months, I have a feeling. Wow, that's like the greatest zit ever popped. Look at that thing. It's still going. Whoa! And is this stuff dangerous now?
It's actually, it's mostly just oxygen and soapy water.
Wow. So no.
So no, but I wouldn't touch it.
All right, good. So all right, I won't touch it then. All right, what else are we gonna do?
So,
that was awesome.
Thank you.
All right, so that experiment was actually similar to the one I just did. That little demonstration, very similar to the one I did. So why did he have a huge zit that popped? Whoops. Why was in this situation,
what grade do you teach?
Elementary.
A huge zit versus mine, which was like a little zit that popped? Why did his explode more than mine? What do you think, guys? Why did he have a greater reaction? Maybe he added more soap. Okay. If I added more soap, it still wouldn't get to that height. Why else? Why else do you think? Maybe he had a bigger crowd to please. You guys are just as good as that crowd. All right. Someone else said he. Oh. What about? Okay. So several answers I have here. He had a greater catalyst. Maybe the sodium iodide was different. Seam said that as well. He had a sodium iodide. Someone else says, or Alex said, maybe more H2O2. What do you mean by that? More volume or more concentration? More volume or concentration we're talking about? Yes. So obviously that reaction, there were Erlenmeyer flasks versus my graduated cylinders. The concentration of the hydrogen peroxide, it probably was going to be a higher concentration to give you that huge explosion. So that was a cool one. That was alpha toothpaste. You could definitely see the heat being generated there in that experiment. If I touched it now, it would have been fine. If you touch the hydrogen peroxide, it will give you a slight chemical burn. I did that early on in my teaching and got a little bit of a chemical burn. What was it like? It took me a while to figure it out because it was like my skin was starting to turn red. Initially, it was like brown, and then it turned red. I'm like, oh, great, got that on my skin. So now I take a little bit more caution with that stuff. Then it irritates a little bit as well. So don't get a chemical burn. Protect yourself. All right, so that's a demonstration. Took us a long time to get there, but we did that demonstration for today. Moving on forward, I'll do a couple more demos on EXO, maybe endothermic in the next couple of days. Examples, Unit 7, Topic 2, potential energy diagrams. Let's get to it. We talked about, I'm going to use this as a guide for today to help me. We talked about kinetics and rates of reactions. We talked about effective collisions. We know what effective collisions are. We talked about rates that affect the rate of reactions. Factors that affect the rate of reaction: concentration, temperature, pressure, and surface area or particle size. Know the 4 factors that affect the rate of reaction. Gases only affect, pressure only affects gases. We talked about potential energy diagrams. We talked about a catalyst is something that speeds up the rate of reaction. Why? It lowers the activation energy and it lowers the activated complex. Speeds up the rate of reaction because it doesn't have to get to as high of a point. We talked about potential energy diagrams. We know the x-axis, we know the y-axis, what they're labeled. We talked about the complex. We talked about activation energy. We talked about the heat of the reaction. Done. That's what topic 2 examples will be on this. And they'll also be kind of on this as well. So I waited to assign topic 2 and topic 3 until I finished up endo and exothermic curves, because you need to figure out the range for those. We know endothermic reaction. Endo means inside. Thermic refers to heat. Heat is absorbed. Anytime you see an endothermic reaction, your heat has to be on the left side of the equation, on the reactant side. If you see heat on the left side of the equation, there's my heat or energy, that's going to tell you it's going to be an endothermic reaction. It's going to have to look like this some sort of way. You have reactants, you have products, activation energy, PE the reactant, PE the products, complex, and then your heat of the reaction. Endothermic reaction. Hopefully you memorize that. You should definitely know that one inside and out. You should know exothermic. Exo means exit, means to leave. Thermic refers to heat. Heat is leaving the system. And in exothermic reaction, your heat is represented on the product side. Your heat, your energy always is going to be on the product side. If you see a chemical reaction that looks like this, you see your heat to the right, that is going to be an exothermic reaction. So again, you definitely should be able to understand the placement of the heat. Is it on the right? If it's on the right, it's an exothermic. Is it on the left? Is it on the left side of the equation? There's my heat right there. It's on left. It's endo. You should be able to differentiate both of those. This equation, exothermic, heat is released. Goes from reactant to product. You should be able to identify all these portions of this curve too. A catalyst speeds up the rate of reaction because it's not going to get as high of activation energy or activated complex. Again, today would be the day in class if we're sitting in front of me in school. I'd give out a piece of paper and I'd say, hey, tell me what kind of curve this is. Label all the portions of the curve inside and out. And I'd probably say, hey, which 2 things are changed with the addition of a catalyst? This is an important curve to memorize. It's not in the reference table. There's guaranteed to be at least 1 or 2 questions on the regions on this curve or endothermic reaction. This is on you to memorize. Maybe you took advantage of last night and you took the napkin at your dinner table and you made one of these and you showed the company you're with what a potential energy diagram looked like or what it meant. I would encourage you to make several of these on scrap piece of paper and label them so you could understand what they mean. That's exothermic reaction. One more thing before I move on forward. Sometimes students have a hard time differentiating between exothermic and an endothermic reaction. One of my past students came up with something which I thought was kind of cool. And I'll give you my explanation of that. So one of my past students talked about and differentiated exo and endothermic reaction in terms of a building. So she said, you have a building, maybe a 4-story building. And on that building, you have different floors, but make an X and Y axes. On that building, you have different floors. 1, oh no, 2. So stories. Guess I didn't do 4. So there's the floors of the building. And maybe she represented, she said, you're at one location first. You're at top of the building. You're at top of the world. So you're at the top of the building, and then what happens? That building caught on fire. So that building caught on fire. That building catches on fire. What the heck can you do? You're going to get the heck out of there. So that building catches fire. You're going to find those stairs. You're going to get on those stairs, and you're going to get the heck out of there. You're going to exit the building. So that building catches on fire. You're getting on out of there. You're leaving. You're escaping. So when heat is added, you're going to escape the building. You're going to leave the building. You're escaping. Exothermic reaction. So you're going to leave the building. This curve represents an exothermic reaction. Exothermic reaction, you start high, it has to get low, and then during that transition, it's going to go through a little change. There's a reactant. There's my product. And you can label everything else. This is definitely going to be an exothermic reaction. Exothermic reaction. Whoops. So that's an exothermic reaction right there. Maybe that helps out. Exothermic reaction, you want to leave the building. Catches fire, you want to leave. You're probably saying, hey, Mr. Brown, you're forgetting something. And I'm going to say, I apologize. This is a nice sunny day. Okay. Exothermic reaction. Maybe that helps. Maybe not. Definitely my best visual for that one. All right. Please open up your examples on topic 2, which is potential energy diagrams. Let's do these together. So examples, again, we do together. Exit pass is going to be graded, and that's for you to do on your own. So example, it's a little out of order here. Topic 2, potential energy diagrams. Cool, no one did it. All right, potential energy diagrams. Maybe you want your notes side by side for reassurance. For the exit pass, I guess you could use them, but obviously on the Regents, you won't be able to use them. So note that you won't have those resources that you have right now. These guided notes that you have, I hope you don't use them on benchmarks. It's a different world. Not telling you can't use them on the exit passes, but I would like if you didn't. You shouldn't have to. I'll say that. You shouldn't have to use them if you do what's expected. Question number 1 says the potential energy diagram. Which letter represents potential energy of the activated complex? Please put the answer in the chat once you come up with an answer. In the potential energy diagram, which letter represents potential energy of the activated complex? I have 26 people on right now. I'll wait for 8 answers. Cool. This group always has consistent answers. That's good most of the time, yeah. So we're looking for activated complex. Find the complex. Complex gets complicated. You have reactant. You have product. If I look at those 2 locations, I know my reactant's higher than my product. It's an exothermic reaction. But activated complex is the highest point all the way to the bottom. Complex, the highest point all the way to the bottom. Choice B is the best answer. So number 1, the best answer is B. Choice A represents potential energy of the reactants. Potential energy of the reactants. Choice D represents potential energy of the product. Potential energy of the product. Choice C is the exact same interval as choice A. That's going to be potential energy of the product. potential energy of the reactant again? One, the best answer is going to be choice B. Number 2, in order for a chemical reaction to occur, there must always be what? Please throw in the chat. In order for chemical reaction to occur, there must be cool. In order for a chemical reaction to occur, there must be effective collisions. There must be enough effective collisions. These two atoms are never reacting. It's not going to make a chemical reaction occur. It's not going to proceed to the forward reaction, the product. These two reactions, two elements, atoms, compounds, whatever they are, if they smash together, correct orientation, smash. If there's enough energy, speed, kinetic energy, then it will move on to the product. Choice A, best answer. Effective collisions between reacting particles. If they're not effective, they just bounce right off. Not enough speed, bounce back. If they're not effective, they're not going to react. Number 3, what kind of energy is stored in a chemical bond? Chemical bond, you probably know this term from 8th grade. Stored energy in a chemical bond is stored energy. Please put in the chat. Stored energy, take a ride on the roller coaster, brings you on up real quick. That's a high potential energy. Why? Because there's a lot of stored energy. So P is high here, but that's just going to shift, transfer the energy as you ride that roller coaster throughout. Potential energy is stored energy. If you have a dam, it's a dam. Put a dam here. In a dam, you live over, don't know the name of that road. Off of the Parkway, East Utica. Oh, in between the Parkway and Valley View. If you live over in that area, in between the Parkway and the Valley View golf course, there's like a dam there. And there's like a lot of sitting water over there. It's by Tilden Ave. Don't know that other road. But if you live over there, or if you know what I'm talking about, there's a lot of water over there by Valley View. You drive up Valley View towards New Hartford, you look to your left, there's a lot of water there. That water was once used for like a backup for the city water, and once was distributed to your house. I was actually talking to a person last night about the water of Utica. Where does it come from? How many different places does it drawn from? We got to have a big conversation about this. But anyways, this water, there's a hill here. It's a little bit higher up than like maybe down Mary Street or down James Street or down Genesee Street. If you look up the hill, there's going to be, obviously, if you're looking up from Mohawk Street, it's going uphill. So back in the day, maybe your house was down here on Mohawk Street. There's your house. But then once you looked up the hill a little bit, you could see the Columbus statue. You could see Valley View, but all the way up in the hill was that little reservoir right there, that little dam. So what happened back in the day, they filtered out the water, they cleaned the water up there, and then it was gravity fed. Gravity's going to pull it down to the drains of Mohawk Street and then come right to your house. It's pretty cool. It's the same type of concept what happens for, I know I'm going off a little bit. It's the same type of concept that happens how we get our water. Our drinking water in Utica comes from Hinckley Reservoir. Majority of our water in the area, in our Utica area, comes from Hinckley Lake, Hinckley Reservoir. So Hinkley Lake is a higher altitude. And then you travel down the highway from North Utica down to Genesee Street. You travel down that highway, it's going to be down. So welcome to Mohawk Valley, the sign is from Channel 4. So come on down, it's downhill. And then you have this city all throughout here. Oops, your city's all there. And all these little buildings, big buildings, whatever, wherever you live in the area, whatever. So what happens, we don't just get this water right to our house. It has to go through a filtration system. There's a plant that takes like all this water in. So this big lake, what happens, the water is going to be now setting to a plant where they clean out the water. They're going to filter the water, make sure it's safe for us to drink. They're going to put fluoride in there. They're going to put chlorine in there to kill bacteria. Fluoride, they like to put that in to help our teeth out. But this little plant right here, after it filters it all out, there's several stages of that plant. Once it goes there, it goes to another tunnel, maybe down to North Utica. I'm guessing it travels. I'm guessing the main inlet would travel from North Genesee Street, all the way down to South Genesee Street, because that's pretty much downhill. So it's going to work its way down, and then it's going to vein out to your road, and then it's going to vein out right into your house. Water main breaks. You hear about it all the time. What happens? These pipes break. Sorry. Get excited about that stuff. I want to tour that plant. Maybe your parents, maybe your mother works at that plant. But I guess they don't do tours now. I'd like to see it, though. I'm very interested. All right, so potential energy. Answer with potential energy after all that. Next up, number 4. Which interval represents the, interval B represents the what? So please put the answer in the chat. Interval B represents what? Interval B, check it out with the curve. That is an endothermic reaction. Definitely. Interval B represents activation energy. The energy needed to start that reaction. Activation energy right there. Activation energy. Activation energy. If you don't get to that high activation energy, this reaction is not going to follow through. Activation energy, try C, best answer for number 4. Number 5, energy needed to start a chemical reaction is called, please put in the chat. The energy needed to start the chemical reaction is called, yeah, a lot of you guys have that. The energy needed to start a reaction is called activation energy, choice C. Number 6, given the potential energy diagram shown, which letter interval represents potential energy of the activated complex? Which one's a complex here? Please put it in the chat. Which letter represents the activated complex? Thanks, Leo. I'll take either B. B is a complex. Activated complex. Top of the peak to the bottom. Complicated. Top of the peak to the bottom. That is definitely an exothermic reaction. Number 7. Diagram shown. Which letter represents activation energy for the reverse reaction? I do want to check this one out. Activation energy for the reverse reaction. All right, so right now we talked about a forward reaction where the reactant yields the product. The reactant yields a product. So it goes from reactant and it follows this direction for a chemical reaction. That's the only one we talked about right now. We know this would have been my activation energy for the forward reaction. That's my complex. That's my heat of reaction. But it wants to know what is the activation energy for the reverse reaction. So forward, cool. Reverse has to go in the opposite direction. So it's got to go from product to the reactant. So it's going from product, there's my product, to the reactant. And then it goes through the reverse process here. So this is the direction it's taking. It's working its way from product to the reactant. Reverse reaction, reverse direction. Product to reactant. It wants to know what is the activation energy for the reverse reaction. For the green reaction there, what is my activation energy? So again, the starting point is still going to be for reverse reaction. It's right there. Starts really right there. It goes through this process. What is the activation energy for the reverse reaction? Starting at the 1, ending at the 2. What's the answer for that? We follow that direction. What's my activation energy? Couple answers. Definitely a tough question. We didn't talk about reverse reactions yet. So now, again, we're just going to look at the flow for the reverse reaction. Reverse starts here, works over to the reactant. So it's following this little direction. Activation energy is the energy needed to start the reaction. Reverse reaction, to start the reaction, we start here. The energy needed to start the reaction is all the way up to there. If we don't get to that high point right there, this reaction is not going to occur. If it does not get to this energy for the reverse reaction, it is not going to go through and follow the reverse reaction. Therefore, the best answer is going to be choice D. D for that one, reverse reaction. We'll see more reverse reactions in the future. So 7, best answer is going to be D. Number 8, 2 particles collide with proper orientation. The collision will be effective if the particles have what? How will it be effective? Proper orientation and has to have something else. Yes, Leo. All right, so it has to have proper orientation, direct hit, but it also has to have enough energy. Which term here, or speed, and energy, whatever. Which term refers to speed? Speed of a reaction. Potential is stored energy. No, it's not that one. Potential is stored. Ionization is referring to the energy needed to steal an electron. Kinetic energy is energy in motion. Activation energy is the energy needed to start the reaction. Kinetic energy is the energy needed. Kinetic energy is energy in motion. That is referring to speed of the reaction. 8 is C. 8 is C. Tough one there. 8 is C. Number 9. Which arrow represents potential energy of the reactants? Potential energy of the reactants. Which arrow represents PE of the reactants? Please put it in the chat. So yeah, you're probably seeing how critical it is to memorize this curve. If you don't memorize this curve, you're not getting these questions correct. It's easy when I have it like that. But again, Regents time, we're not going to have that setup. I don't know what they're going to do. No idea. I don't know. Is it going to be an online test? Is it going to be a live? I don't know. But I would guess for Regents, you're not going to have this ability. Potential energy of the reactants is going to be choice B. B. Potential energy of the reactants. A would represent activation energy. C's complex, activated complex. D's PE of the product. B's PE of the reactants. Next up, last question, number 10. The collision theory states that a reaction is most likely to occur when the reacting particles collide with the proper, what? Easy question there. Please put in the chat. Yeah, proper energy and orientation, proper kinetic energy, proper speed, proper orientation. They love orientation. Choice D, the best answer for that one. Somebody asked me, do you think we'll have a Regents? I hope we do. I hope we have Regents. I'm not slacking. Hopefully you're not slacking on your end. I want you to show what you learned. I don't know if that's selfish. I want you to express what you learned throughout the year. I want to see if you actually, or this routine, different routine, was effective. I don't want to waste a year not knowing. Did you learn anything in chemistry class? Number 9, someone asked what the question answer was. P, the reactants, choice B. I don't know. I really don't know if we're going to have the Regents or not. Since we're not mandatory for graduation, lots of times people don't need chemistry in order to graduate. So that, I don't want to say it, but chemistry might be one of the ones they might cut. If they were to cut any Regents, they might cut chemistry, they might cut physics, because they're not 100% necessary for graduation. You need bio, you need earth. Don't need chemistry. That's why you guys are here. You're here because you want to be. But if you want advanced Regents, you need this course. Advanced Regents Diploma. All right, those examples, you could submit them. You don't have to submit them. We're good to go with that. All set. The rest of the class today, I'm just going to give you time to work on the exit pass for topic number 2. So find topic number 2, exit pass. And let's see here, exit pass topic 2. If you could handle, you understood those questions right there, then you're definitely going to be able to understand these questions on the exit pass. So from now to the rest of the class, there's 12 minutes. There's, I think, 10 questions here on potential energy diagrams. 10 questions. You have to work on this exit pass. Please complete it. Once you're done, you're free to leave. If you want to leave, just know that this is due on Saturday. If you're going to hang out for the rest of the class, totally fine. I'm going to ask that you join a breakout room. And in the event you have any questions, please feel free to ask. I'll help you with 1, 2, 3, 4, 5, whatever many questions you need in order to understand the topic. If you leave, have a great day, make decisions, and we'll see you next time. If you hang out, please join the breakout group by yourself. Oops. Have a great day. If you leave, see you later. If you have questions, feel free to ask for help.